Okay, so that's the schedulability of the real-time systems. So these all assume that these processes are happening periodically. What happens if I have a periodic events? Okay. Sometimes, yeah, it might happen. I mean, I don't have any guarantees that I'm going to run every 200 milliseconds, 500 milliseconds, but the basic idea is the same. Basic idea is the same. You can't use more than 100% of the CPU. Okay, it has to be lower than that. And engineering such system is harder. The simplest one is most common one is this one. Everybody has an allocated slot, and you run only in that slots. That's it. Okay, so these are the real-time systems. Really, I mean, I'm not going to talk much about them. At the end of this chapter, we are going to talk about this thread scheduling. Okay, if we are doing the scheduling at the user level, okay, at the user level, then this is what happens, right? I mean, at the user level, I can say that for the process A, I can schedule thread number 1, 2, and 3, 1, 2, 3, etc. I mean, there is nothing I can, there is nothing, nothing more than I can do, okay? More than this, I can't do. But if I am doing it with the kernel level scheduling, I can do this intermixing, right? I mean, I can do this kind of stuff. I have 3 threads here, 4 threads here. Okay, I can do run A1, this one, then B1, this one, then A2, then B2, and etc. So I can intermix between these threads because each one is a different thread for me, the kernel. This one is not like that, okay? You schedule A1, A2, A3, A1, A2, A3. When you switch from process A to process B, then it becomes B1, B2, B3, etc. Okay? So as you see, the thread scheduling is more flexible if you do the kernel level thread implementation. But this time, okay, question. Which one is more expensive, switching from A1 to A2 or A1 to B1, or is it the same?
No.
We say,
Sorry.
say it again.
Uh, A1 to B1 is more expensive. Should be more expensive
Why?
because in threads inner the process they use the same address, but
Are this
different processes different address. I mean different memory address.
are there spaces? It
Yes.
uses a different address space. Yeah, that's true. I mean, switching from A1 to B1 requires you to switch the address space too, and switching the address space is expensive. Why? Well, I'm having context switch here too. I mean, A1, A2 context switch is cheaper than A1, B1 context switch. And our classmates say that it is different address space. So why are different address spaces more expensive to switch? It is true that A1 to A2 is cheaper. A1 to B1 is more expensive, way more expensive. And the real reason is the address space are changing, but changing the address space is expensive. Why?
Because stack pointer will erase the address value and gives the new value to address space. each time when
Well,
the
it's
process
this,
switches.
it's the same thing for the A1 to A2, right? I mean, if you don't save your stack pointer and reload the new one, then you can't run your new thread anyways. So it's the same thing, exactly the same thing. In terms of stack pointers or any other registers. In terms of saving the registers and loading them again, it is the same cost. It's not the register, it is something else. When you change the address space, the cache, L1 and L2 caches, they all have to be invalidated. Why? Because I cannot keep the cache contents the same, okay? They have to invalidate it and cache has to be repopulated. In that case, it's going to take lots of more time to invalidate the cache and repopulate it again. And that's going to take lots of time. That's why kernel level threads, even though they can do this, okay, they don't want to do this much. They like to go this way. First, schedule between the threads of this process, then switch, then schedule between those. But if needed, they can do this too. Okay. When we look at the memory, memory abstraction, we are going to see this even better. Okay. So, okay, what else we can say about those? Thread scheduling. Since the kernel knows that switching from thread, okay. Kernel knows that switching from a thread from process A to process B more expensive, then it takes this into account too. Okay. And this one is nice. Sometimes we like user level threads better than kernel level threads. Why? Because I can do application specific thread scheduling. Okay. Remember our threads. Remember our threads running on a web. Let's go to the beginning. Let's go to the beginning. Threads. Where are my okay, these are the threads. Yeah. Remember this one, a multi-threaded web server. I have thread number 1, thread number 2, thread number 3, and thread number 4. This is a dispatcher thread. This gets the web page address from the customer, okay? And it says that, okay, I'm going to dispatch one of you, worker threads. Worker threads are real servers. This one will take the request and assigns a dispatcher thread for this one. So if you are scheduling these 4 threads, okay, what would you do? If thread number 2 blocks, would you schedule thread number 3 or 4 or 1? After thread number 2, let's say thread number 2 blocked. Which one would you schedule? 1 or 3 or 4? It's a simple question. 3 or 4 are equally important. They are just worker threads. But 1 is different, right? Without one, the whole system goes down. We have to stay interactive. When we receive a new request, then I have to handle it immediately. Okay? So usually with these kind of thread scheduling systems, I schedule it like 2, 1, 3, 1, 4, 1. So what I'm trying to say here is, if I do this with a kernel level thread, okay, library, kernel level thread library, 1 and 2 and 3 and 4 are no different. They are simple threads. But if I do it at the user level, because I am writing my own thread scheduling algorithm, I say that one is way more important than others. That's what we are saying. That's what we are saying here. Okay. Suppose a worker thread has just blocked and the dispatcher thread and the two workers are ready. Of course, I like to schedule the dispatcher thread. Okay, so that's the whole thing. That's the whole I like to say about the thread scheduling. It's no different than process scheduling. The only thing that I need to be careful about is which one is causing more overhead time, okay, between process or in process switching. Good. At the end of the chapter, about inter-process communication, there are two classical problems. One is the dining philosopher problem. The other one is the readers and writers problem. I like to look at these. Maybe these are not very common problems that you see every day, but they are classical problems and they are interesting. Very nice compact solutions they have. I like to talk about those. Let's say I have 5 philosophers. Philosopher number 1, philosopher number 2, 3, 4, and 5. Well, P means process, right? They are really processes. Each philosopher or each process, I am going to call them processes, okay? Um, so uh, each process is either thinking or eating. If you think, I mean, if the process thinks or if the philosopher thinks, then it doesn't need anything, just does some computation. But when they eat, they need to take this fork and the other fork. Okay, they are eating spaghetti. Okay, so to eat the spaghetti, this philosopher needs 2 forks. Okay, you need to get these 2 forks. These are actually in computer world, these are our resources. Resource number 1, resource number 2, resource number 3, resource number 4, and resource number 5. What are the resources? For example, this is a scanner and this is a printer. This process will scan documents and it will do something on the document and it will print it. Something like that, okay? So to be able to continue, this process needs to get this resource and this resource at the same time. But these resources has to be shared between the processes, okay? I have 5 resources and 5 processes, and these all have to be shared, okay? So when it comes to philosophy, thinking and eating, we say it that way, but when we think in terms of processes, process 1 is computing and is doing input output, for example, for the eating. For doing input output, it needs to take both of these, R5 and R1. But sometimes R5 is used by P5 along with R1. So that means what? That means P1 and P2 cannot be eating at the same time. P1 and P5 cannot eat at the same time. Why? Because this is not shareable, right? R5 is either it will be used by P1 or P5. So let's look at this one. P1 and P5 cannot be active at the same time. P1 and P4 can be active at the same time, right? So question for you now. How many philosophers can be eating at the same time in this case?
Two.
At most two, right? Yeah. Because P1 and P4 can eat. P1 and P5 cannot eat at the same time. P1 and P3 can eat, right? But P1 and P2 cannot eat at the same time. So it is two. So I need to come up with an algorithm, okay, that doesn't cause any race conditions that will let this happen. Okay, so they can think as much as they want. Thinking doesn't require any resources or forks, but eating will require resources or forks, and you have to share your fork with your neighbor. Okay, so here is a solution. 5 philosophers. For each philosopher number I is running this infinite loop. Okay? Each one is running this loop. They think, after they think, they take the fork number I. This is philosopher I. Let's say this is philosopher number 3. This one will take the fork number 3. And it will take the fork number 3 plus 1 is 4. Modulo 5 is 4 again. This is fork number 4. If I can take both of them, okay, I will eat. After eating, I put the forks back and I will think. Okay. Sounds nice, but let's be careful about this. There are 5 philosophers. Okay, there are 5 philosophers, and each one is running the same function. So this I is both 1 and 2 and 3 and 4 and 5. 5 of them running the same function. 5 of them is running simultaneously. Let's say um, process 2 and 3. Okay, process 2 and 3 are running at the same time. Okay, process 2 is running. It came here. It took the fork number 2. Okay, switch happened. Why don't I do this? So the process 2 is running and it took the fork number 2, right? And switch happened. Process 3 started running and it took the fork number 3. Switch happened again. Switch happened again. Process 2 is trying to get the fork number 3, but it can't. Why? Because it is taken by process number 3, right? But before that, process 3 started running. P4 started running. Okay, P4 took the fork number 4. Switch happened. Process 3 is trying to get the fork number 4, but it is taken. So the fork number 4 is taken. Before process 4, started running, P5 started running, and you know where I am getting at, right? So at the end, P2 will be waiting for P3, P3 will be waiting for P4, P4 will be waiting for P5, P5 waiting for P1, and P5 will be waiting for P2. Okay? So that's what's going to happen. So there will be a deadlock. There will be a deadlock, and that's not a good thing. We should prevent it. That's why this is not a good idea. A non-solution to the dining philosopher's problem, right? A non-solution to the dining philosopher's problem. Do you have any suggestions to solve this problem?
Of course, in the little area.
Exactly, yeah. Let's use some semaphores. Exactly. Mutual exclusion, right? I am going to do this. If I lock this, okay, put a lock in here, right? Come on. Mutex. Down mutex. And if an up mutex. So what it says, I say that take fork I and take for I plus 1. But before I take fork I, switch happened. No other philosopher or the process can enter the critical region, right? So they cannot take anything, right? That's true. So I take fork number I, and I take fork number I plus 1. Okay. Both of them, it is done atomically. It's not done atomically, but doesn't matter if the switch happens or not. If I am inside this region, I am guaranteed to have fork number I and fork number I plus 1. And I would eat. After eating, I would release it. Okay? And I would release it. So the problem doesn't happen. Let's see what happens. So P1 is running, P2, P3. Let's run this. It's not like dining philosophers 5, but let's do it with 3. Okay? So it is much simpler. Okay? So P1 runs, okay? Takes the fork number 1. This is, let's do it in a circular way. P1, P2, P3, fork number 1, 2, and 3. So P1 took this one. P1 took this one and this one. And it is, well, no, I can't do it with this 3, right? It has to be 5, right? It has to be 5. Sorry. Then in that case, let me do it this way. Let me do it this way. Let's go to this one. Okay, so P1 took this one and took this one. Okay. So let's think about this, if it is working or not. How about this one? let me ask this question first. If I do this up mutual exclusion, is this good? Is this any good? I say that after thinking, I am going to get the lock. I will take my forks if I can take them, if I get a mutual exclusive zone, and I will eat. I will put my forks back. Is this a good solution?
This way, at most one philosopher can eat at the same time.
Yeah, exactly. And that's a bad thing, right? I mean, it doesn't cause any race conditions. It doesn't cause any deadlocks, but only one philosopher can eat at the same time. That's not a good solution. Okay, it doesn't cause any deadlocks, but if P1 is eating, it is using these two resources. Okay, no other, including this one and this one, no other philosopher can eat. So that's not a good solution. So we eliminated that one. How about this one? This one is a bad idea too. Okay, so after I think, before I eat, I take my forks, fork number I and fork number I plus 1, both of them, and I eat and I put them back. So what is the problem here?
One will try to take fork before other puts the fork.
Let's say yes. Let's say P1 is, let's say P1 is, P1 is eating. So it took both forks, R5 and R1, right? It took both of them. Then P5 is trying to wake up and P1 is eating. So P1 took fork number 1 and 5 and it is eating. Then P5 is trying to, okay, it is trying to get the forks R1 and R5. Sorry, no. This is 1, this should be 4. This should be 4, right? Okay, so P5 is trying to get 4 and 5, right? It's trying to get 4 and 5. It will get 4. 4 is available. Well, first of all, it can go into this critical region. Why? Because P1 is in the eating process. So it will get 4, fork number 4, but fork number 5, it cannot get it. So it will get blocked inside the critical region. So it holds the lock for the mutual exclusive region. It needs the fork number 5, but it cannot continue because P1 is holding. So P5 is blocked. It is waiting for the fork. So P5 is blocked, which is nice because it cannot continue anyway. But now P4 wanted to eat. So P4 needs fork number 3 and fork number 4. It cannot take fork number 3. Why? It cannot take any forks. Why? because P1 is eating, P5 is blocked inside the critical region. P4, even though it can continue because both of these forks are not used, it cannot continue. Why? Because it cannot enter the critical region. Exactly. Because it cannot enter the critical region. Critical region is held by process number 5. And process number 5 says that I am waiting fork number 1, right? I took fork number 5. Sorry, I took fork number 4. I am waiting for fork number 5. It is held by process number 1, and I cannot continue. So it is blocked. So it's not a good idea to use a single mutual exclusion rule, okay, to define two critical sections maybe. One is here and one is there. Or maybe I don't need the critical sections here, no. So either I am going to move this to this place. In that case, I can't use two processes at the same time, okay, which is not good. Or I need to find a solution, okay. So did everybody get the problem for the solution? If all of them start at the same time, this is not a good solution. Okay, if I don't have any mutual exclusion, the original is not a good solution because if all of them started at the same time, the first one took the fork number 1, second one took the fork number 2, etc. It's not a good solution. It's not a solution actually. If I use mutual exclusion this way, it prevents other valid processes from using the resources. And if I do it the other way, if I do it this way, then again, it is preventing others using the same. It is preventing others from using the available forks. So we need to come up with something. So this is a classical solution. This is what we are going to do. Dining philosopher's problem. Let's look at this algorithm. I have n processes. My left is defined this way. You understand this, right? It's a very simple modular arithmetic. Left is I plus n minus 1. Okay. So if my I is 4, then 4 plus 5 minus 1 modulo 5. So it is 8, 3. It is 3, right? So my left is going to be 3. For the right, it is I plus 1. I plus 1. So 4 plus 1 is 5. 5 modulo 5 is 0. So for I for left is 3, right is 5. Okay. Okay. Okay, so I can be in any one of these situations, 0, 1, and 2. Thinking, hungry, and eating. Okay, as a process, I might be thinking or hungry or eating. Okay, and my semaphore is a simple integer, but the thing is that I can up a semaphore or down a semaphore. Upping semaphore is just increasing it, downing it, decreasing it, but when it is 0, then it blocks. We know that. For each philosopher or process, I can be either thinking, or I am hungry, or I am eating. So I invented this state now between thinking and eating. I like to eat, but I am not eating. It is hungry. Okay. And there is a mutual exclusive zone, mutex. And for each philosopher, there is a semaphore. So initially, all of these are this is a 0, 0, 0, 0, and 0. Okay. For each philosopher, there is a semaphore, a separate semaphore. Okay, so these are the data structures that I'm going to use. Good, okay. So the philosophers, they all do this. They think, they take forks, eat, and they put forks back. Okay, thinking and eating is trivial. And we are going to look at these take forks and put forks. This is where the tricks are. Okay, so each of them is doing exactly the same thing. Take the forks and put the forks. But take forks is not as straightforward as take fork I and take fork I plus 1. It's not. Okay. It will be a little bit different. Okay. So this is take forks. Okay. Before I take the fork, this is my critical region. My critical region is here. I down the mutex and I up the mutex. Okay. So inside my critical region, I say that my state is hungry. It is not eating yet. Okay. It is not eating yet. My state is hungry. Then I am calling a function named test I, and I release the lock. And after that, I try to down this mutex of Si. Remember, the Si is initially it's all 0. It's all 0. Okay, so that means what? If I try to decrement this Si, I will get blocked here. So there must be something inside this test I to make it positive. Okay. For the put forks, I am going to skip it for now, but let's get this one. Test I. Should I put them side by side? Yeah. Okay. So state I is hungry, test I, and up. Let's look at this test I. For philosopher number 3, if my state is hungry, well, I did it that way, right? Yeah, my state is hungry. If my left is not eating, okay, if my right is not eating, so that means what? If my left is not eating, if my right is not eating, then I can eat. I am eating, right? Both of those resources are available. And I up my semaphore. I up my semaphore. So let's look at this one. So this one's tested. If I am hungry, if my left is not eating, if my right is not eating, then I up my semaphore. Okay, my semaphore became 1 now. Okay, then I up this mutex. Then I up this mutex. Okay, and after that, I down my semaphore, so I can continue, right? If nobody else is eating, then I am fine. I can do this. So what is the solution about this? How does it prevent from not using? Well, first of all, if my left and right is eating, if my left and right is not eating, let's look at that one. I am fine. But if my left is eating, right? What happens if my left is eating or if my right is eating? I will say that when it comes back, this will be blocking here, right? Because SI is 0. I didn't update my SI. See this one? SI, I didn't up SI because my left or right is eating. I didn't increment this SI. Since I am trying to decrement SI now, I will get blocked. So I am waiting until my SI is incremented. So I will get blocked here if my left or right is eating, if both of them are eating. Okay, so that's the idea. So who is going to up this SI? Let's look at this put forks. Put forks this way, it works this way. Again, this is my critical section. I say that, okay, I'm not eating anymore. State I will be thinking, well, this is interesting to see what it does. Test left and test right. In take forks, I just tested it for myself. This one says that test it for the left and right. I stopped eating my left and right. I am going to test them. If my left is hungry, if my left's left is not eating, if my left's right is not eating, then my left's state should be eating and up the semaphore of my left. And do it for the same thing for my right too. See, this put forks calls this function for left and right. Okay, it's not calling it for itself. This one, take forks calls it for itself, but for this one, it calls it for its left and right neighbor. Okay, this is called dining philosopher's problem, and this is a simple looking but very elegant problem, the solution. And it solved the problem. Let's try to see what happens if all of them, let's try to see what happens if all of them try to take the forks at the same time. Okay, they all started. Okay, only one of them will take the mutual exclusive lock. So only one of them will say, I am hungry, I am hungry. My left is not eating, my right is not eating, it's going to take one. So only one of them can take the forks and start eating. Okay. Once I start eating, one of the others will take the mutex. If its left or right neighbor is eating, then it will be blocked here. So how many places where I can get blocked? It is either this position down or this position. Let me use red pen. This position or this position or this position, right? So this down is only for mutual exclusion zone. This one is waiting for the forks. Okay, waiting for the forks. This one will be released when my left or right neighbor tests me when they release the forks. They say that if my left or right is not eating, then up the semaphore of my neighbor. Okay. Good. Any questions on this? Again, this picture has nothing to do with philosophy or eating or anything about food. P's are for philosophers, forks are for the resources. Printers, scanners, database records, files. For example, an input file and output file. I need to get lock on both of them because I am modifying them, etc. Good. Can you suggest any other solutions? First of all, would this happen if situation is like my table is like this? My table is like this. It's not circular table, but a rectangular table. And I have a fork here, fork, fork, and fork, fork, and fork. These are forks. I don't know what kind of forks, but this is philosopher number 1, 2, 3, 4, and 5. Does this problem happen if I have such a configuration? 5 philosophers and 1, 2, 3, 4, 5, 6 forks. Would I have a problem in this case? Original solution. Where is my original? Yeah, okay. Let's put it in here. Is this solution valid for this algorithm? Yeah. Where is everybody? Okay. Do I have the same problem in this picture too? It's not a circular dining table anymore. It's a rectangular. And I don't have 5 forks, I have 6 forks. Do I have the same problem here?
The problem may be because if one eats, two cannot eat again, but this time, 3 of them can eat at the same time.
But 3 of them say you can eat at the same time, but I'm just asking is this algorithm okay now? Is it? What was the problem? All of them are taking their forks, fork number 1. Okay. None of them will take fork number 2. Well, is that correct? No, it's not right. All of them will take fork number 1. Okay. This one will take 1. This one will take 2, 3, 4, 5. But the philosopher number 5 can take fork number 6, right? 5 and 6. And it will eat and it will continue. It will eat and it will continue. Once it is done, 4 will take it, then 3 will take it, 2 will take it, and 1 will take it. It's not a deadlock, but it's a bad situation. Why? Because even though 3 of them can eat at the same time, only one of them can eat it from time to time, right? So not exactly the same problem, but the problem of not efficient resource utilization is here too. Okay, I prevented maybe the deadlock, but I am not as efficient as I can be. So this solution can be applied here, and this solution, okay, can be applied here, and it will be okay. At the end of the chapter, there is another classical problem, readers and writers problem. The problem is this, okay? I have a database, and I have reader processes, reader process 1, reader process 2, reader process 3, reader process. And how many processes can read how many processes can read the same database at the same time?
All of them.
All of them can read it, right? Because reading is not a problem. I can read them, all of them. But if I have writer process 1, writer process 2, ... writer process M, how many writers can write to the same database at the same time? Only one, right? You cannot write to the same database using two different processes because that would cause some data inconsistency. So come up with some kind of inter-process communication mechanism, synchronization mechanism that will let any number of reader processes on this database or just single writer process, okay? Either many readers, okay, or just a single writer. That's called the reader-writer problem, okay? And this is the algorithm for the reader. This is the algorithm for the writer. I don't have time, but, well, I mean, we are doing this online anyways. So let's look at the writer first. Writer says that I am thinking of data and I'm going to write it. Mutex, a semaphore, down database and up database. If I can take this lock, I will write it and I will up it. That's it. So that means what? If I have this lock, no other writer can have the lock. Okay? And if I have this lock, no other reader can have the lock. This is as simple as this. Okay? Just simple mutual exclusive lock. Okay? A binary semaphore. That's it. DB. So that's the writer part is the simple one. Reader part is a little bit different. Readers say that if there are many readers inside the database, that's okay, I can read it too. But if there is a writer, then I can't continue. I should say that. Okay. This one say that if nobody is accessing the DB, then I can do it. So let's look at this one. So there is a mutual exclusive zone. There is a database lock, and this is the reader count. Initial 0. So this one doesn't use any mutex. This one uses the mutex of the DB. Let's look at this one. Down mutex. This is the first critical region. Okay, and this is the second critical region. Down mutex, up mutex. Say that get the mutex. Okay, get the mutex. Increment the reader count by 1. I am the reader. Okay. If the reader count is 1, that means what? Previously, nobody was reading it. So I'm trying to get the database. I'm trying to get the database, the lock for the database. If I have the first reader, I should get the lock the database. Okay, then up the mutex. Since I get the database, I can read it. If RC is if RC cannot be 0, right? Here, because I incremented it. If RC is 2, 3, 4, 5, I don't down it because I already got it as a reader, right? So second, third, fourth, fifth readers, they will not try to get the database lock because one of the readers got the lock anyways. I read the database, then again, I am going into the critical region. I decrement the database reader count by 1. If RC becomes 0, then I release the database lock. So this is smart. This will let as many readers as possible into the database. As long as the first one gets the lock, then I am fine. If the first one gets the lock, the writer will have to wait because writer cannot get the lock. If the writer has the lock, the first one cannot get in. Only the last reader will release the lock. Okay? Good solution. But there is a one classical problem about this solution. It doesn't cause any race conditions. It doesn't cause any deadlocks, but there is a problem about the writers. Writers may, if there are too many readers doing the reading all the time, writers may starve, right? Because once the readers start reading, the one of them will read and it will release the lock. The other one will read, it release the lock. But always, if there is always some reader reading the database, writer will never get this lock. Okay, so there is a starvation issue here for the writer. Okay, good. So that's the end of this chapter, chapter number 2. Are there any questions? Okay, if there are no questions, then I will continue next tomorrow. Okay, I don't like nobody's asking any questions. And how many people are there in the audience? Let me see. There are 93. Tomorrow morning, I will start the lecture with a simple quiz. Okay. Make your cameras ready. I will make a quiz, online quiz. For the in-class people, if you are coming to the class, I will take your quiz on a paper. Okay. You are not asking any questions. And the quiz will be about, of course, the processes, chapter number 2. Okay, tomorrow morning we will start with the quiz. Okay, see you tomorrow.
See you.
Do you think?
Bye.